This is a chart from Hyperphysics. It describes Steven Weinberg's first 3 minutes. Basically, it's got a chart here where at 0.02 seconds after the Big Bang, the temperature was 10 to the 11th Kelvin, and the energy per particle was 8.6 million electron volts. They've got that same information at 0.11 seconds, 1.09 seconds, 13.8, 3 minutes, 3 minutes 46 seconds, 34 minutes 40 seconds, and 700,000 years. So according to this model, as early as 1/10 of a second into the universe, the matter in the universe had become resolved into individual protons and neutrons. And I'd kind of like to understand exactly how that information was achieved. I don't have access to that book right now, so I'm going to try to do my own calculation. Mainly because I think at 0.11 seconds, the universe would have a density far, far greater than even the density of a neutron star. And it seems hard for me to believe that nuclei such as helium is going to form under those conditions. So what would be a good way of estimating exactly what the density of the universe was after 30 seconds after the Big Bang, or 30 minutes after the Big Bang? So what I would suggest is taking a group of stars that are currently available, that we can tell where they are within a certain region, and then extrapolate back to how close those stars must have been when the universe first started, about 30 minutes after the Big Bang. Take this mass of all of those stars added together and divide by the volume that would have been occupied by these stars just 30 minutes after the universe began. So I'm going to try to come up with what sounds like a frequently asked question. How many stars within 100 light years? And I find some things on Google. Well, here's an answer from NASA's Imagine the Universe, which gives 63 stars within 5 parsecs and 3,496 stars within 25 parsecs. The fall-off in density is probably due to the fact that many stars are too faint to be cataloged at a distance of more than 5 parsecs. At still larger distances, the density of stars does vary as you move outside the local spiral arm of our galaxy and into less populated regions above and below the disks. However, they go on to go ahead and use the highest density there to calculate what they think is the star density for 100 light years. My own intuition says most of the mass out there we can't see, so I would be inclined to also use this larger density to get an estimate for my purposes. So the next question I want to ask is, what is the mass of an average star? Now this website says the average star weighs 10 to the 32nd kilograms, while the mass of the Sun is 2 times 10 to the 30th kilograms. Now, I think that sounds totally... No, that's not a good answer. That goes under the assumption that the average star is 50 times bigger than the Sun. 50 times. So I'm not going to accept that answer. In fact, I'm going to go in here and say I do not think that answers the question. That is ridiculous. In any case, because I use such a large number for the number of stars, I'm going to just use the mass of the Sun as the average and not use 50 times the mass of the Sun as the average. So here's our basic question. We have our current density of 0.120 stars per parsec cubed, and the mass of the Sun is 2 times 10 to the 30th kilograms, so we're just going to multiply those together to get a density of 2.4 times 10 to the 29th kilograms per parsec cubed. And now I basically want to find out what the linear contraction is if it was between 30 minutes and 13.7 billion years. Basically, you can imagine a cone shape, and this, we can imagine the way the universe is now, which is just say velocity times 13.7 billion years, and the width of the cone then, which is the velocity, the average velocity times 30 minutes. So basically, to get the ratio between these lines, we need the ratio between 30 minutes to 13.7 billion years. My cat just walked across my keyboard, and this is what she typed. Thanks, Kiki. I don't even know how to do that, but she apparently knows. So I'm going to string together a bunch of conversion factors here. There are 10 to the 9th years per billion years. There are 365 and a quarter days per year. There's 24 hours per day. And there's 60 minutes in an hour. That means that the length of any scale then was 4.16 times 10 to the negative 15th times the length of any scale now. And the volume is going to be reduced by a fraction, or is going to be cubed of that. So volume now. So whereas now we have 2.4 times 10 to the 29th kilograms in 1 cubic parsec, then we had 2.4 times 10 to the 29th kilograms in 7.22 times 10 to the negative 44th cubic parsecs. Now I'm using Google's quite convenient calculator to find how to convert this into SI units. So I'll be multiplying 1 parsec cubed by, or I'll be multiplying this density by the 2.938 times 10 to the 49th meters cubed per parsec cubed. And that leads us to a density of 1.13 times 10 to the 23rd kilograms per meter cubed. Now, for reference, the density of water is 1,000 kilograms per meter cubed. So this is somewhere around 10 to the 20th times the density of water. Now I'm going to glance around and see if I can get an estimate of the density of a neutron star. This guy says it's approximately 6.65 times 10 to the 14th grams per cubic centimeter. Now I'd like to convert that grams per centimeter cube by multiplying by 100 centimeters per 1 meter and cube that, and 1,000 grams per 1 kilogram, which gives us 6.65 times 10 to the 17th kilograms per meter cubed, which means that this density, which was the density of the universe after 30 minutes, is about 170,000 times greater than the density of a neutron star. Now, Steven Weinberg claims that the universe was producing protons and neutrons in this state. Protons, neutrons, electrons, and everything else. I kind of think that since the density here is 170,000 times greater than that of a neutron star, that it was probably quite a bit of time after that protons and neutrons began to form in the universe, and that in fact in this era we probably had an entirely different form of matter involved. Some kind of primordial superparticles that may have still been as big as galaxies or stars in themselves. some kind of high mass, high energy particles that there is no way we could ever hope to produce in a laboratory environment.